In this video, we're going to talk about linear functionals and the joints. Linear functionals and the joints. So let's go back to some previous definitions. You recall uh, a linear transformation, and I'll just put it right in front of here since this is just review. A linear transformation from a vector space V to a vector space W is a function T from V to W such that T of X plus Y is equal to T of X plus T of Y, and T of Cx equals CTX for all scalars C and for all X and Y's in V. We can also, these properties could also be stated this way: TCX plus Y is equal to CTX plus TY. So this and these two are equivalent definitions. You can either do it in 2 steps or in 1 step. Now, linear functional is a specific type of a linear transformation. So a linear functional from a space V into a scalar field. So linear transformation goes from the vector space V into a scalar field. In other words, you put in 2 vectors and you get out a scalar. And it obeys these properties. Fx plus y is fx plus fy, and fcx equals cfx, same as the definition we just had, except, again, the output this time for these, for a linear functional, the output is not a vector, but a scalar. And once again, you could also say this in 1 step, or f of cx plus y is equal to cf x plus f y, like that. So once again, these are equivalent definitions. These two, that is equivalent to this. So that's the definition of a linear functional. Again, the idea is it's mapped into a scalar, not into a vector, like the more general linear transformation. Now we want to go to say about some things about linear functionals. You can define a linear functional this way. Let's say, for example, we may define let's say we call this f maybe of, say, x is equal to x y for some fixed y in the vector space V, where what we have here is an inner product. In other words, you can create a linear functional with an inner product this way. Let's say you fix this y, some vector in V, and then for every x, you can define this functional as x, y, where this is the inner product. And again, there's lots of ways to write the defined linear function this way. You could have used g, say of z. You could also define the linear functional this way. You could say g of z is equal to z w for some fixed vector w in V. Again, the idea is you're putting in a z and getting out a scalar. So you're fixing w, so you can put like any value of z1 in here, and you'll give different scalars for this fixed w. So same thing up here. This is a linear functional where y is fixed, put in different values of x, keep getting out different scalars. Here, this is a linear functional. This w is fixed, put in different values of z, you get out different scalars. So again, now this is not the only way to define a linear function. You could define it in any way that will obey those properties that we talked about, those linearity properties, but this is one way to define it. And sometimes they might even define them this way. You might say, put like a little, let's say a little y here, for example, x equals x, y for some fixed y in V. So you might, so a lot of times they might even put this as a subscript here to kind of say what the fixed vector y is here. You could write it this way, but the idea is you put in a vector, get out a scalar. And there's a theorem that we have related to this. Let V be a finite dimensional inner product space. Recall this is a vector space with an inner product defined on it. And f is a linear functional on V then there exists a unique y in V such that f of x equals fy. So the idea is, you have some linear functional, just defined somewhere else. So it's a linear functional on V. You can turn it into the type of linear functional we've defined just a minute ago. In other words, so if you have a linear functional, you can always find a unique vector in V such that you can define the linear functional this way, x comma y, where you have this inner product here. So you can turn any linear functional and define it this way. There's always a y that'll make this work. And we're going to use that in the following theorems. For any linear operator T, on a finite dimensional inner product space V, there exists, I'll use the symbol for there exists, a unique linear operator T star on V such that this is true for all x and y in V. So there is this linear operator that does this, and we call this the adjoint of T. So for any linear operator on a finite dimensional product space, there exists this unique operator. It's called the adjoint. This is a very important operator that we're going to use much more in linear algebra, called the adjoint of T. And so when you're working with inner products and you're working with linear operators, you can always do this operation here. T of x, y is equal to x t star y, where t star is the adjoint. And let's actually go through the proof of this. Let y be any vector in V, then y prime of x is a linear functional on V. So basically we have this. So let y be any vector in V, and then we can define a functional like this, that y prime of x is txy. So we're defining, say, this linear functional in this way. We're saying you put in an x, you apply the linear transformation t, and this with y, this defines a linear functional. So we can simply say txy is a linear functional on V. And now by the previous theorem, there exists a unique vector, and let's call it, just for convenience, call it y prime in V, such that y prime of x is equal to x, y, like this. So let's see what we have so far. First, we define this linear functional this way. And so now we have this linear functional, and we're calling it this. And by the last theorem, we said, if we have a linear functional, we can find a unique vector, and this time we'll call it v prime, y prime in V, such that x, y, and that should be y prime, x, y prime is equal to this linear functional. So now, since we have this linear functional up here, and we have the same linear functional defined in this equivalent way, putting these together, we can say that txy is equal to that. So we can say that those things are equal to each other. So note, note something important here. Note, for every y, such a y prime exists for this particular t. And let's do one more thing. let's call this y prime t star y, i.e., y prime is equal to t star y. So we've just redefined the name we have. We're calling this. Then finally, if we go back up here, finally we have tx, y, x, y like this. So we have defined the adjoint as we had said we wanted to do. So this is the adjoint. Now we have to determine, is this t star linear? Is it a linear transformation? In other words, is our adjoint is it a linear transformation? So let y be equal to z plus w for z and w in the vector space V. So let's start with that. So let's start with this. And again, let's do our definition here. We showed that the adjoint is defined this way. So we can work backwards and say this is t x z plus w. And then we can, this part here, since it's an inner product, we can do this. And now, once again, using the definition of the adjoint, we have this. Now use the definition of the inner product. We have this. So now you can see, look at our first step, this is equal to this. Yeah, sorry. So this is equal to this. Now that's one part of proving something is a linear transformation. And then the second part, let's see, be a scalar. We have this, and use the definition of the adjoint. We have this. And then from the definition of the inner product. Now, again, let's assume maybe we have a complex inner product. So let me do it in the most general case. So if we have a complex inner product, if we're taking something out of the second term, we have to put a conjugate sign on top of it. But if it's real numbers, that's just going to be C. And then, so this is, again, from a definition of the inner product. And then down here, again, use the definition of the adjoint. Like this. Finally, the definition of the inner product. Like this. So we have, if we compare this with this, we have this. So our adjoint is a linear transformation. So the most important thing to come out of all of this is that the adjoint T star of the linear operator T obeys this with the inner product that we have T of X, Y is equal to X T star Y, like that. This will be used over and over again in linear algebra. Now, if our linear transformation T is in the form of a matrix, then T star is the conjugate transpose of T. So if our linear transformation T is in the form of a matrix, then T star is a conjugate transpose of T. So, for example, if we have a case where, let's say, something like this, then of course, if you have upper T like this, then T transpose, of course, is going to be, remember we interchange rows and columns. So the first row, when we take the transpose, becomes the first column. Second row becomes the second column, etc. And then the conjugate of that is 1 minus I minus 2I 3, 4. Of course, the conjugate means we change the sign of the imaginary part. If we had a negative here, it would have been positive. If the i's are positive, then we change them to negative. And so, for example, I'll use a real simple example where we can see this real easily. I'll just use this example where our inner product is the dot product. And let's define our operator again. I'm just going to keep it something simple. Let's say we have these two vectors. Like this. Then if we take txy, that's defined as this. And if we work this out, we end up with 222 dotted with minus 6, 8. That'll give us minus 12 plus 176 is 164. On the other hand, if we do this, where this is the conjugate transpose, again, this is the adjoint. Like I said, in the case of a matrix, this would be the conjugate transpose. And we put this together. This is going to be 5 minus 1 dotted with. Now we want to take the transpose of this. That'd be 1, 4, 3 minus 2 minus 6, 8, like this. And this is going to be 5 minus 1 dotted with 26 minus 34 gives us 130 plus 34 is 164. So that's just a simple example to demonstrate that if we have a matrix and we have two vectors, txy is equal to x, the adjoint y, where this is going to be the conjugate transpose. And we got 164 in both cases. couple more things. A few more properties here. Have to do with the adjoint. Let BV finite dimensional vector space. There's going to be inner product space. If T and U are linear operators on V, and C is a scalar, T plus U adjoint is equal to T adjoint, U adjoint, C T adjoint is equal to C conjugate adjoint T U adjoint is T like this. Is T. And again, these are linear operators. They're not necessarily matrices, but they're the general linear operator. If you have the sum of two linear operators and you take the adjoint, that's equal to the sum of the adjoints. If you take the joint of some scalar times T, you'll get the conjugate C times the adjoint. And if you take the adjoint of this product, you'll get the reverse in the adjoint of each of these. And the adjoint of the adjoint gives you the original operator back. And of course, some of these are pretty common. Most of these you have in other contexts, like, for example, you have the transpose obeys this rule. The transpose obeys this rule and this rule. And also, this is common if you have a matrix that has an inverse, you get this. The inverse of the product is the inverse of the second one times the inverse of the first one. Now, if we have the case so if a linear operator is equal to its adjoint, then T is called self-adjoint or Hermitian. Now, if T is a matrix and it's Hermitian, then T is equal to its conjugate transpose. So, for example, let's say if we have something like this, T equals maybe -7. I'll take a real simple example. 4 minus 7. Let me do something different. 9i for plus 9i. So let's say if we have an example like this, then notice the transpose of t is going to be minus 7, 4 plus 9i, for minus 9i, 4. And if we take the conjugate of that, get minus 7, 4, 4 minus 9i, 4 plus 9i. So there's an example where t is equal to its conjugate transpose or its adjoint. T is Hermitian. Now for any linear operator, t we may define say u1 is 1/2 t plus its adjoint. And then let's consider the adjoint of that. So we've defined u1 this way. Now take the adjoint of that and see what happens. So again, remember, if there's a constant here, we can take it out and do the conjugate of that. And then you remember on the inside, we have this plus this. Remember, whenever we are summing two linear operators and have the adjoint, we have to apply it to this and this. And of course, the conjugate of a real number is just the number itself. Then we have this. And then, of course, also whenever probably the adjoint of the adjoint is the original linear operator itself. And so we have t like this. So notice that, so u1 is equal to its adjoint. So u1 is Hermitian. So anytime that you have a linear operator, you can create this linear operator and it will be Hermitian. Also, you may define u2 this way and take the adjoint of that. Like this. And again, do all of our rules. Remember, if we have a constant inside, we can bring it out and find the conjugate of that. Then apply this in here. And this here. Once again, the adjoint of the adjoint gives us the original operator itself back. And of course, here, this is going to be in negative in the denominator. Now we can just bring it, apply it to the whole fraction. Then here, minus t. We can bring this negative inside. And so we'll have negative of the adjoint and positive t. So we have u2 is equal to its adjoint. So u2 is Hermitian. Like this. So that's another way that you can get a Hermitian matrix or operator. Could be a matrix, or it could be just a linear operator by defining it this way. Then finally, something interesting you can do with both of those. U1, U2 defined this way. We can say that our original operator T can be written as U1 plus I U2. And of course, this works because you can say, put these in, let's say U1 plus I U2. And let's see, we had U1 was defined as 1/2 T plus T conjugate, or T adjoint. One over 2I. And this is multiplied by I. So let me put that up here. T minus T adjoint. So again, I applied the I right over here. So you can see those cancel. 1/2 T plus adjoint. And this is one, there should be a 1/2 there too. And again, these are going to cancel. So we're going to have T minus 1/2 T adjoint. Those two are going to cancel. Then we'll have 1/2 T, 1/2 T equals T, like that. So T can be defined that way. And again, this, if it's in terms of, if T is a matrix, this is called Cartesian decomposition, when you can write T like this, where U1 and U2 are defined the way we define them.